Hello, in this video I'm going to look at a future value of an ordinary annuity. Now, by definition, an annuity is basically a sequence of periodic payments that are made that can be annually, semi-annually, quarterly, monthly, daily even. Um, and it's mostly just so that you can save that particular amount and spend it, for instance, or even set up an account that you'd like to have at the end of some period. Now, let's say, for example, that you would like to deposit $500 at the end of every year for 5 years. So let's just say that you have a principal amount. That amount is $500. Let's say that the annual interest rate is going to be 8%. Now, let's say that in this particular example, this is going to be where T is 5 years. Now, because we're going to deposit it at the end of the year, that would imply that the period is going to be M. Now, the easiest way to kind of just think about this is in regard to the cash layout. So, for example, you have 0, you have 5. Okay, so we have 1 year, 2 years, 3 years, and then we have 4 years. So for every single year, we know that there's going to be an amount of $500, $500, $500, and $500. Okay, now the things of which that we do not technically know is how much interest is earned for each period. Now, the way of which that we're going to do this is we're going to think back to our equation of how do you find the future value? Well, the future value is given by P times 1 plus R over M raised to the MT. Now, this is where it gets a little interesting. So, for example, we can say that the sum of the payments that you make are going to be S. Now, for the first year, well, for the first year, you have that that amount that is going to be compounded. Well, no interest actually basically applied. So in that case, you're just depositing that 500 at the end. So nothing gets earned. But then you have for the second year, it's going to be 1.08 multiplied by your 500. Then we raise that to the 1. Now that basically you've had that amount has sat for an entire year extra, you have that's going to be 1.08 to the second because again, you're compounding the amount that was already earned. And then you're going to repeat that process until you basically reach the end of your deposits. Now, in this case, the end of the deposit is at the fifth year, but you'll notice that it's 1.08 raised to the fourth power, not the fifth power, but the fourth power. So in that case, like all that we need to do is just basically add all of this. Now, in our calculator, we can actually do that. So 500 plus 500 times 1.08 plus 500 times 1.08, that's going to be squared, plus 500 times 1.08. This is actually going to be cubed, right? And then we have another amount, 500 times, right? 1.08, and that's raised to the fourth power. Now we push enter, and we get that the final amount that is earned is $2,933.30. So, okay, well, that wasn't too bad in terms of the computation, mostly because I know that I can enter in a, you know, computation into a calculator, and it's going to do it for me. Okay, so now in this case, we need to figure out how much interest was earned. Well, you made basically five. potentially you made 1, 2, 3, 4, 5. So you made like 5 different deposits. Now, in this case, you have that the interest in this sense is going to be, um, so you have the 2,933 and 30 cents minus, well, okay, there was 5 payments being made basically. So that's going to equal to 433. So 5 times 500, and you get 433 and 30 cents. Okay, so that's not too bad. I mean, and that's money that is completely yours. Uh, and you have this interest amount. Now, of course, you can increase the amounts by making larger deposits and so on. But what if you did this over not 5 years, but 10 years, 20 years, and so on? What if it was compounded more than once? What if it was semi-annual? Well, in that case, the computation becomes more excessive in that sense. So we try to think of like, is there a better way to do this? And there actually is, if you think about it. So the way of which that we think about this is that what if you had your sequence of payments and you had R plus R multiplied by 1 plus I, that's going to be to the 1. Now 1 plus I is the amount that's being well, that's the compounding amount, and that's the R, the payments. So you're going to repeat this process until you reach the last payment, which in this case is 1 plus I. But think about it like this. N, because like if we go back to our formula, this is usually N. So in this sense, N is going to be just one smaller. Why? Because you have one less payment. Now, let's say that we multiply this by 1 plus I on both sides. So you have S times 1 plus I, and that's going to be R times 1 plus I plus R times 1 plus I to the second power. Now, what ends up happening is that this last one ends up being R times 1 plus I to the N. Okay? Now, here's where it gets a little tricky. Okay, so what I'm going to do is I'm going to subtract these two. So when I do that, I'm going to actually end up with, let's see. Okay, so I'm going to subtract S. So S times 1 plus I minus S is equal to, okay, so basically we have that everything else will cancel out essentially. So we'll end up with R times 1 plus I to the N minus just R. Okay, so in this case, like just notice that these two cancels out. We can do that. So that cancels out, that cancels out. So everything cancels out leading up to these last two. So we're left with the difference of these two, the R and this amount right here. Now, in this case, we end up with that the formula ends up becoming S times I equals to R multiplied by 1 plus I to the N minus 1. And we'll just put like a little bracket right there. But then now you have that S, which is the sum of your payments, is going to be R times, okay, this is where it looks a little weirder, plus I to the N minus 1, all divided by I. Now, basically, this formula right here represents the future value of an ordinary annuity, where the payment is made at the end of the period. So S is basically just the future value, R is the periodic payments, and then I is really the same thing. So like, so S is the future value, and then R is the periodic payment. And then I is equal to R over M, and then N is equal to M times T. Now, these parameters are basically the same as you kind of know them. Now, most of the time in some textbooks, we tend to just use the following as a way to simplify, uh, like, kind of like make it more obvious, where we have that this is 1 plus R over M raised to the MT. Well, yeah, we could probably just leave it as I, and then raised to the N minus 1, and then this is divided by I. Now, it's up to you, like, if you want to, replace these variables respectively, like where you're like, okay, well, I remember that I is just R over M, and then I remember that N is just M times T. So in this case, this is more or less the exact same thing. Okay, so we call this future value of an ordinary annuity. Now, if you think about this, this is no different from saving up for like, a car or a washer or anything like that. So normally you'll use this formula for those types of things because you'll just try to think, is this money that I'd like to have or is it money that I'm going to owe? Now let's look at an example. Um, okay, so we have that Kevin decides to deposit $100 at the end of each month into a savings account, earning guaranteed interest rate of 4.5% compounded monthly. What is the value of this annuity at the end of 10 years? Okay, so primarily, the main thing that you have to look for is the key words, which in this case is savings, and then at the, well, annuity, of course. Um, and then we know that it's at the end of each month. So first off, we can use that the payment is $100. The R is going to be 0.045. The T is equal to 10. And then, let's see, what else do we need? The M. The M says that it's going to be 12 months, so you have that it's 12 months. Okay, so let's go ahead and put this into practice where we say that the future value is equal to 100 multiplied by 1 plus 0.045 divided by 12 raised to the 12 times 10 minus 1, and all of this is divided by the interest amount, so 0.045 divided by 12. Okay, now if you want to enter this into your calculator, you just have to know how to use the appropriate number of parentheses. So like, you know that you need that in its own, and then, well, this one's already accounted for. So let's see. If we go ahead and we do this, then we'll just do this. How about we go ahead and we put 0.045 divided by 12, and then we raise it to the 12 times 10, and then we're going to have that subtract 1, close it, divide by parentheses 0.045 divided by 12. Okay. Now this gives us 15,119 and 81 cents. So that's not bad when you think about it because it's monthly. You're depositing that and you probably won't even notice it. Um, Let me see that that's correct. Yeah, and 81 cents. So we round up instead of down. Okay, now that is basically the future value amount essentially. So in this case, like if you wanted to know the interest that was paid back or earned, it's basically just going to be the future value amount, so 15,119 and 81 cents minus how many payments were made. So you made $100 and then you deposited 12 times for 10 years. So you basically take this amount, subtract the 100, multiplied by the 12 payments times 10 because you did it for 10 years. And okay, so 3,119 and 81 cents. So okay, so this is the amount of interest that was earned over a 10-year period, which basically says that, you earned uh, you know, not really more than, I mean, it's not really that much when you think about it, but really, it's good, because it's money that you're not going to owe, essentially. Now, hypothetically, you could have probably cash outlaid the entire amounts and figure out like how much is the current value. But that's probably more difficult, to be honest, like if you do it that way. Whereas like it's a lot easier if you just do it this way, because you have a formula, you just plug it in and so on. Now, sometimes you may come to the point where you know that the amount that you would like to have, and this is very common because, you might be like, okay, I'm gonna be graduating at the age of 18, and I know that I need to have an amount for college or for a car or for an apartment. So in this case, like, when it comes to finding the amount that you need to save up for, you basically just kind of consider this. If you know that the sum of the payments is equal to r, and that's going to be 1 plus I to the n minus 1 divided by I, then it makes sense just divide by the entire bracket to solve for the r. So r is basically equal to s times I divided by 1 plus I to the n minus 1. So in this case, this is what we call a sinking fund. So this is basically whenever we know the amount that we need. So if we know that we need $20,000 to save up for a car, then in that case, we know that we can solve for R. But it's granted that we know other bits of information, for example. So let's say that we do an example of finding a sinking fund. Okay, so okay, and remember that sinking fund is basically where we just need to find the periodic payment because we know that we're going to have some amount or big expense that, uh, we'd like to have that money. Okay, so for example, you have that Jordan and Angela decide to start a college fund for their newborn son, Jared. They estimate that they will need $100,000. So already I know how much is required. It's $100,000. So we know that S is equal to 100,000. Now, they deposit into an amount that pays 6%, so automatically I also know that that's 0.06. Now, they're going to be compounded monthly, so we have that M is equal to 12. Now, the amount of time that this is going to take is 18 years. So essentially, they're just starting right away. uh, they're starting right away to set up this account because remember that the more time that you allow, the more amount that it'll grow or that it'll grow to. And then plus, it makes the deposits shorter or smaller. So we know that we're going to use the formula R equals to S times I divided by 1 plus I to the power n minus 1. Now, this is more or less a very complex computation, but it can be done. So 100,000 multiplied by zero point zero 0.06 divided by 12, and all of this is divided by 1 plus zero point zero 0.06 divided by 12 raised to the 12 times 18 minus 1. Okay, now this computation might seem a little robust, but we can do this like in a way that it's not going to be too bad. So we can do this in steps, by the way. Okay, so that's going to be divided by 1 plus zero point zero 0.06 divided by 12. Okay, so this amount needs to be for 12 times 18 and then minus 1. Okay, so theoretically this should work. Okay, so we just hit enter. And 258 and 16 cents. So that's going to be 258 and 16 cents that the family, Jordan and Angela, need to deposit to have $100,000. Now, of course, hypothetically, the child, if they choose to go to college, then in that case, I'm guessing that it's assumed that, the person is going to spend about $25,000. Is that right? Uh, yeah, $25,000 per year, which means that the student would have potentially like 12,500 per semester, which I guess in a way is it's kind of enough for a student especially. But it's almost like having like a part-time job if you think about it, that the student doesn't have to do. But also look at it like this. That family is spending less than $300 per month, and it's almost like a car payment essentially. And that's not to mention, that they might have extra amounts that they're paying towards. But, the whole point of this exercise is that you realize that that's not really a lot when you kind of think about it. And if you want to know the interest that was earned, basically you just take the amount that they deposited. So we can find 100,000 minus the 258.16 multiplied by 12 times 18, and that's going to be the amount of the interest. So basically 258 and 16 cents multiplied by 12 times 18 minus the 100,000, and that's like yeah, 44,237 $237 um, and four was it 44 cents. Okay, so this is 0.44 cents. Okay, so that's the amount of interest that was earned. Okay, now you could probably look at it like this, like, okay, like how much really was put in, if you wanted to, but hardly ever do we ever think of it this way. Usually we just look at the interest because it's more interesting to look at the interest. So, okay, so the family did put about half in, almost, a little just more than half, and their net gain was the $44,000. So it's almost like they doubled it, if anything, if you want to think of it that way. That's one way that you can possibly think of it in terms of like, you know, if uh, if you wanted to look at the interest that was earned. Now, it is possible, for example, to kind of Like, let's say, for example, that you wanted to know, like, how many years will it take to reach this amount if you know the payments. So, in some cases, you may have that for instance, you know the future value amount, and then let's say that we don't know something. Like, we have that there's the payment, and that's multiplied by the 1 plus the I to the n minus 1 divided by I. Now, most of the time, you have that one of these components would be missing. So, for example, if you happen to know that there's a amount of 15,000 that you would like to have, and then you know that the amount that is deposited is, let's say, like 500, and you know that it's going to be like 1 plus, let's say, 4%. So like 4% divided by, I don't know, let's say monthly, for example. If I said annual, I'm sorry. Um, but let's say that we don't know the year. So it would be 12x minus 1 divided by 0.04 divided by 12. So in this case, we don't know how many years it's going to take to reach the $15,000. But algebraically, you can actually figure this out just by plugging into your calculator. So, like, for example, if I happen to know that I have, let's just clear it. Okay, so $15,000. I have 500 multiplied by parentheses. Um, let's go ahead and use alpha because that'll just make it cleaner. And then we'll just put 1 plus 0.04 divided by 12. And all of this is raised to the 12x. And this is going to be minus 1. And then down over here, we have the interest that we're going to put. So 0.04 divided by 12. And then we're just going to close it. Now, mind you that we're looking for x. So let's do this. Let's make the window somewhere between maybe like 50. And then for this, we could probably just make it 25,000. And then let's just go ahead and graph. So we see that the intersection point is right down over here. So we'll just do second trace intersect, enter, enter. And it looks that it's going to take less than 2 years. So that's like 2.4 months, or 2.4 years, sorry. So so in that case, you have that x is approximately 2.4 years. So in that case, like if you kind of think of it this way, you have that zero point 0.4 times 12. That equals about 5 months almost. So in this case, you have that it's going to be 2 years and 5 months, such that this amount will accrue to $15,000. Now, there actually is another way to do this, and that would be probably like maybe like making like an Excel file, but you know that's gonna take too long in that case, like to see like how it adds up to 15,000 just by doing the file. Um, which I mean you don't want to be too dependent on that, to be honest. Okay. That's gonna be it. And you know, you could have easily used this in Desmos, by the way, but you don't really have to.